When I wake up in the morning, love, and the sunlight hurts my eyes, and something without warning, love, bears heavy on my mind.
Hello and welcome to the Longhorn Racing 2021 Unveiling. My name is Kevin Meckler and I'm the president of Longhorn Racing. This year, we're very excited to celebrate our first time unveiling our vehicles virtually. But we also want to recognize that it's our 40th. That is the 40th anniversary of Formula SAE, which started here on this campus in 1981. That year, there were only 4 teams competing, one of which was the University of Texas. But today, that competition has grown with over 100 teams competing this year. Longhorn Racing in that period of time has also adapted. We have gone from having just 1 team to 3 design teams, building electric, combustion, and solar-powered vehicles. All of our students have been working so hard with building these vehicles, and 2020 was no exception. We're so excited to share with you what we've done, and with that, I'm now going to pass it on to James Garcia to present the combustion vehicle.
Hello all. I'd like to take the time and thank all of you for watching our unveiling event today. My name is James Garcia and I am the team captain for Longhorn Racing Combustion. Before I begin, I would like to thank the university, the faculty, our corporate partners, friends, and family. Without all of your support, we would not be able to do what we do and provide students with such a unique engineering opportunity. Thank you. The development of this car has not been without challenge. We are still in the midst of a COVID pandemic, and due to this, there has been very little work in person. Despite these challenges, the team has been able to design a car that we are all proud of. In the summer of 2019, after the FSAE competition, we as a team decided to revamp the entire design process of this next development cycle. The reason for this was that the designs that were previously used were iterations over years of old designs without proper design documentation or design philosophy. The development of the car was split into 4 major systems: body, dynamics, electronics, and powertrain. Each system had set specific goals in the beginning that aligned with the design philosophy of the car while maximizing performance of the vehicle. To expand on this more and certain aspects of the car that the team had decided to spend time developing, each of the system leads will now provide a brief overview of certain projects on the car that they felt made most impact.
In the past, this design team has created a series of unnecessarily heavy cars that share a lot of the same designs as their predecessors. This year, we wanted to take a step back and re-examine these designs. We found that a significant amount of unnecessary weight was present in the wheel assemblies. Generally speaking, whichever car has the lowest center of gravity, the lowest yaw moment of inertia, and the lowest mass will be the fastest. This year, we switched from 13-inch diameter wheels to 10-inch diameter wheels, as this significantly reduced unsprung weight, and the tires on a 10-inch wheel come to operating temperature a lot quicker. We also selected new wheel bearings that are far lighter at the expense of bearing life, which isn't necessary for Formula SAE cars as they have short lifespans and are easily maintained. This transition was difficult because it forced us to design within a smaller space that exists within a 10-inch wheel. Another way we were able to reduce weight was through the use of topology optimizations. Topology optimization allows for the optimal geometry to be determined by a computer algorithm for a part subjected to a specific loading. In the future, we will be looking towards this design solution for most of the components in the dynamics system.
Hi, my name is Rajul Nanda, and I'm the Electronic System Lead for Longhorn Racing Combustion. This year, the electronic system focused on two major projects for the car. The first is a drive-by-wire system to replace a mechanical throttle cable, and the second is a telemetry project which will allow us to have more robust data acquisition capabilities. The first project, the drive-by-wire system, was made possible due to a very generous donation from eControls. eControls donated a top-of-the-line Bosch electronic throttle body. This system confers many advantages for the car and for the team. Firstly, it will allow us to have a customizable throttle curve for each driver. Secondly, it will allow us to more efficiently tune and calibrate the engine. And, most importantly, it will allow us to eventually implement throttle control and traction control. The telemetry project, on the other hand, allows us to have more robust and more accurate data acquisition capabilities. These new data points will allow us to more efficiently tune our lap times and will allow us to make design improvements in the future. Overall, the electronic system is the newest and the coolest of all four systems. Along the way, from doing these two projects, we have also developed a new wiring harness, have debugged tire simulation code, and have started developing a driver's display. I would like to thank the team for all of their efforts this year, and would now like to hand it off to Nathan Ion, who is the body lead. Thank you.
Hi, my name is Nathan Ion, and I'm the body system lead engineer. This year, our student engineers designed a functional yet elegant body package comprised of an ergonomic design, a lightweight frame, and minimal but effective aerodynamic elements. The body system works together to provide a stable and comfortable driving experience. A major goal for our chassis design team was to reduce the weight of the vehicle while preserving its structural integrity. This was achieved through rigorous torsional rigidity analysis and structural load testing. Integrated seamlessly with the vehicle chassis is the driver ergonomic system. This subsystem was designed to keep the driver safe while promoting the vehicle's usability and functionality. Keeping that in mind, this year we introduced a paddle shifting system in collaboration with a powertrain system, making shifting quicker and removing the need for the driver to take the hands off the wheel at any time. The minimal aerodynamic elements allow the vehicle to maneuver through tight corners and long straights. After a rigorous testing and analysis campaign, the team was able to reach desired downforce targets while minimizing drag. All combined, these systems work together to push the vehicle towards peak performance. And now to Blake.
My name is Blake Titel. I'm the powertrain system lead. The overarching goal of the powertrain system is to optimize acceleration at the exits of the characteristically low-speed corners of an FSAE track. To do this, we broke down our engineering process to first principles. This is exemplified by our creation of a one-dimensional engine model, which allows us to precisely optimize the outputs of the engine by changing various design parameters. Our designs were further optimized using CFD flow simulations. The result of these simulations and optimizations is an intake manifold that experiences 20% fewer aerodynamic losses than the previous manifold design. This intake design features a clover-shaped plenum with a torpedo fin-inspired air divider that both provide a clear path for air to flow from the plenum to the runner. Like the intake manifold, the fuel tank was also 3D printed out of nylon by Cumberland Additives, which allowed for more compact packaging and reduced the weight by nearly 70% compared to the previous aluminum fuel tank. With all the quantitative accomplishments the powertrain system contributed towards increasing vehicle acceleration and improving power delivery, we also managed to decrease our weight by over 10%, or 24 pounds, since 2019. Thank you for joining us today, and now on to the electric team.
Hello, my name is Christopher Zumalin and I am the team captain for the Longhorn Racing Electric Formula SAE team at UT. Before we talk about the car, I want to first introduce our student leadership for the 2021 season. The aerodynamics lead is Sean Habibi. The driver controls lead is Srinidhi Tupuri. The dynamics lead is Daniel Wynn. The powertrain lead is Joseph Vickery. The electronics lead is Sachin Desai, and the race strategies lead is Jake Highland. Now, all of our leads and students on the team this year have put in countless hours to design, manufacture, and test the vehicle that we are about to unveil to you today. When this team was founded back in 2016 with only 15 members, we had a dream of being one of the best Formula SAE electric teams in the country. And I'm very happy to say that today, I think that we are very close to achieving that goal. With over 100 members, we have placed 7th overall at the 2019 Formula SAE competition in Lincoln, Nebraska. And we were one of only 4 electric teams to compete in every single dynamic event at that competition. In the 2020 design presentation, we placed first in our design bay at the 2020 virtual competition. And I look forward to making that a repeat in the 2021 competition. Now I'm going to talk about the 2021 vehicle performance targets. When we designed this year's vehicle, we designed it with one goal in mind: first place at the competition this summer. In order to obtain such a lofty ambition, we knew that we'd have to redesign our vehicle from the ground up. We began by looking at the vehicle's weight targets. We revised the targets for every single system of our vehicle, and we created a weight reduction of 16% overall from the previous year's vehicle. In order to set our new targets, we based them primarily upon other teams from previous years, as well as the lap simulator that we developed in-house for our own team. Based upon our research, we knew that we had to have an acceleration event time of at least 3.5 seconds and a skid pad time of 5 seconds. In order to obtain this, we went through many different configurations of the vehicle from a powertrain, aerodynamic, and dynamics perspective. We determined that the optimal center of gravity for the car would be a 60% rear distribution at 12 inches above the ground. For the powertrain of our vehicle, we will be using an MRAX 228 medium voltage motor with a 5:1 final drive ratio in a rear-wheel drive configuration. For the battery architecture this year, we've transitioned from a rear-mounted battery to a flat-pack battery that goes underneath the driver. We have significantly increased the aerodynamic downforce of the vehicle this year with the addition of an under tray and a full redesign of the front and rear wings of the car. Doing so will increase our cornering speed without significantly reducing our top speed on the straights due to excessive drag. In addition, we've updated all of our aerodynamics package from a fiberglass layup construction to a carbon fiber construction that will significantly reduce the weight of the overall aerodynamics package. Finally, we are transitioning from 13-inch to 10-inch rims to significantly improve the handling of our vehicle. And now I'd like to pass it off to Daniel Wynn to talk about the dynamics and structures of our vehicle for this year.
Hi everyone, my name is Daniel Wynn and I'm the Vehicle Dynamics and Structures Lead for this year. Today I will be talking to you about the design and innovation behind our suspension, frame, and unsprung assemblies. The general theme of this year's design has been ease of manufacturability, simplicity, and an ability to tie design intent to measured track performance. And you'll be seeing that in the designs I'll be talking about today. I'll start off with the suspension. At first glance, the suspension seems relatively conventional. We're running a double wishbone setup with a pull rod in the front and a push rod in the rear. The suspension system also includes an ARB in the front to allow for roll adjustability. But if you look a bit more closely, you'll start to see what sets our suspension design from this year apart from other years. There's the addition of a large sensor suite across the suspension. These include load cells in the front and rear to measure normal loads on the tires, as well as accelerometers, shock potentiometers, and many other sensors to help us tie measured track performance back to our anticipated simulation results. We've been working hard on developing a 5-mass nonlinear dynamics model, and being able to validate some of the results through suspension testing would be invaluable for not only tuning the setup of this year's vehicle, but also adjusting designs of future cars. In the unsprung system, we've been trying to address issues that we've had with fatigue and reliability in the past. We've had several hubs and uprights fail due to improper fatigue design before, and we've adjusted this year's design accordingly to try to rectify some of those issues. For instance, in our hubs, we're utilizing a new preload method to more uniformly load our cross roller bearings and increase the bearing life. Additionally, we've been using better FEA models and boundary conditions to simulate our hubs and predict failure better than we have before. Finally, on our frame, we've been working hard to lower the overall CG of the vehicle to hopefully reduce the load transfer and cornering and take faster corners as a result. We've changed to a floor-mounted battery as opposed to a battery mounted in the rear in the past, and this has lowered the CG of the vehicle drastically, allowing us to take corners much more quickly than before. This has also necessitated a frame that is more capable of handling some of the impulse loading in corners. And we've been working hard to improve the torsional rigidity to reduce the coupling between the front and rear sides of the frame in accordance with those higher loads. That kind of summarizes the major design changes that we've made in the dynamics and structures system this year, and I hope that gives you a good idea of our system. With that, I'll pass it off to Joseph to talk about powertrain.
Hello everyone, my name is Joseph Vickery and I'm the powertrain lead for Longhorn Racing Electric. The main goal of our powertrain system this year was to reduce weight and complexity whilst optimizing our performance. At the heart of our powertrain, we have the battery, which consists of 480 Samsung 21700 40T cells, which give us a pack voltage of 400 volts and a pack capacity of 6.9 kilowatt hours. These cells were chosen for their high volumetric efficiency and ease of packaging, which is very important in our switch to a flat pack battery. 2 air intakes and 16 fans on each side of the case are used to cool our battery by flowing air laterally through each segment. This system is capable of removing up to 3.6 kilowatts of generated electric heat. The drivetrain architecture that we chose is a single motor rear-wheel drive system with a chain-driven differential. The motor and differential are mounted vertically for ease of accessibility and assembly whilst keeping them as low as possible. Our motor is an MRAX 228 medium voltage liquid cooled, and our differential is a Taylor Ace Mark II automatic torque biasing limited slip differential. With our chosen gear ratio of 5:1, we're able to achieve a top speed of 70 miles per hour, peak wheel torque of 1200 newton meters, and continuous wheel torque of 625 newton meters. Our motor is cooled by 2 radiators mounted on either side of the car in the rear and a water pump. This is capable of dissipating 3.8 kilowatts of heat. I hope this has given you a good overview of our powertrain system, and now I'll pass it off to Sean to talk about our aerodynamics package.
Hey y'all, my name is Sean Habibi and I'm the aerodynamics lead for LHRE. We had a really simple goal for aero this year, and that was to produce the maximum amount of downforce possible to help increase our cornering speeds. After many hours of research and simulation, we created a multi-element front and rear wing with our own custom airfoil design. We also designed the wings to be adjustable too, which helps us tune the car to a specific driver's preferences. Lastly, for the wings, we switched from fiberglass to carbon fiber to make the wings both lighter and stronger at the same time. The greatest upgrade to this year's aero package is the addition of our undertray and our diffuser. We decided to take advantage of all available space for aero components. The undertray and diffuser are by far our most efficient aero parts on the car, and they give us about 30% more downforce with only minimal drag and weight penalties. This year's aero package is lightweight, robust, and is sure to reduce lap times. Not only that, but it makes the car look great too. Now back to Chris to wrap things up.
While the 2021 season has been a very serious challenge for our team, I have been constantly impressed by our ability to overcome those challenges and create a seriously impressive race car this year. I'm constantly reminded of just how amazing and how hardworking all of the members of our team are, and I want to personally thank y'all for all of your hard work this year. In addition, I'd like to personally thank the Cockrell School of Engineering, all of our corporate partners, and all of our families and friends who have helped us get to where we are today. Without your support, none of our students would have this incredible opportunity as part of an amazing design team.
Hello, my name is Michael Wolf, and I'm Longhorn Racing Solar's team captain. Our team was founded in 1989 by a passionate group of students and advising professors with the hopes of building a competitive solar-powered car. Our first generation vehicle was named Texas Native Sun, and it competed in the 1990 GM Sun Race from Orlando, Florida, all the way to Warren, Michigan. Nowadays, our competition exists in 2 phases, the track race and the cross-country race. Our track race will likely be held at Circuit of the Americas, the F1 track here in Austin, and it will be used to qualify for the cross-country race. Since the inaugural car, we have completed an additional 5 vehicles, and we are now well on our way to the 7th generation. That car is slated to be finished in time for the 2022 summer competitions, a little over a year from now. Over the past year, our team has gone through an extraordinary amount of change, both from the COVID restrictions, but also from beginning a new build cycle. I'm happy to say that through this trial by fire, we have rebuilt the team and gained an extraordinary amount of knowledge on vehicle design. We pulled on our past experience from our last car and iterated on every part of the build cycle, from design through manufacturing. We have focused on 3 key themes since the beginning of this new project. Our first major theme is to plan, and plan some more. We've started a master plan scheduling system that details the major objectives that we need to hit each month all the way out through race time. We've also started a monthly plan system, which specifies the work and projects that we need to finish each week. On top of these 2 systems, we've also pushed the mindset of accountability and hitting deadlines. This new culture has been instrumental in our success so far this year. The second major theme is building the knowledge. Since a member can only stay on the team for 4 years, it is absolutely critical that the older and more experienced members can pass on what they've learned. To facilitate this process, we've documented every part of our design cycle on various platforms like Google Drive and OneNote that will exist for generations of students to come. On top of this, we've built our membership base from 20 members in the summer to about 50 members today. Altogether, over half of our membership is underclassmen. That means that when older and more experienced members graduate, we can have other experienced members take their place. The third and final theme is return to first principles thinking. First principles thinking is a way of solving complex issues by designing simple solutions using engineering fundamentals. Now, we've set 2 overall goals in line with this theme. The first is to pass all scrutineering and regulations checks at our track race. The second is to complete 1 lap at Circuit of the Americas. To accomplish this, we've designed our car specifically for ease of manufacturing and assembly, plus the added documentation I've already mentioned. These key themes have brought us out of the design cycle successfully and into manufacturing. Now I'd like to introduce the solar team leadership, the people who are really making this happen. First up is Chase Block, our chief engineer, who's a 3rd-year electrical engineering student and general god of all things. When someone says some nonsense, he's usually the first person to catch it, which is why he's a great chief engineer. Our electrical systems are led by Rishi Ponakanti, a 2nd-year ECU student who's also the czar of all in-person electrical work. Fun fact, he grew 3 feet over quarantine. Hannah Lee, our power systems and hardware lead, is a 2nd-year ECE student. She's also one of the most detail-oriented people I've ever met. Clark Poon, a 3rd-year ECE student, is our incredibly hardworking BPS lead. He also drives a late 2000s model Honda Odyssey, which makes him the electrical systems team mom. Afnan Mir, a 1st-year ECE student, is our array lead, with humor drier than the West Texas desert. And finally, we have Roe Gall, our controls lead, who's a 2nd-year ECE and also taking 19 hours of classes. Our mechanical systems are led by Sonia Lopez, a 3rd-year mechanical engineering student, and she's really taken charge over our manufacturing efforts this year. She also speaks Japanese. Walter Stark, our body lead, is a 1st-year mechanical engineering student with a superhero last name and more 3D printers than I can count. John Ching, our dynamics lead, is a 4th-year mechanical engineering student with an awesome off-roading Jeep, and also he's a military vet. These are the people who are really making solar run smoothly, and I wouldn't want to compete with anyone else. There are just a couple items on our car this year that we'd like to highlight because we think that they truly embody our team's innovation in solving our competition's challenges. To talk more about these designs, I'll pass it off to our chief engineer, Chase Block.
Our competition is one of endurance, and so a lot of thought has gone into weight and power savings. We want to be able to drive all day, and that doesn't happen unless we use less power than our solar array takes in. The array itself is comprised of 260 silicon monocrystalline cells arranged on top of the vehicle. This is the most that our competition will allow us to have. Each cell is about 23.6% efficient, but that efficiency goes down when they're combined into modules. The array itself is comprised of mini modules, which are just arrangements of cells in either a 2x2, 2x4, or 1x4 arrangement. These modules have been created over the past 2 years by members of our team who have soldered and laminated these with EVA and Teflon. The solar array is in reality 2 arrays, each of which have several modules wired in series. To generate the most power possible, our solar array team has been working on the development of a maximum power point tracker, which is a system that monitors the power production of the solar array and automatically adjusts the electrical load on the array to generate the maximum power at that time. This is necessary because of the highly nonlinear characteristics of solar cells. We expect our array to provide about 875 watts. There's enough time to talk about all of the electrical systems that will be in the vehicle, but I'd like to point out that nearly everything is custom. Aside from the motor controller and the motor, We have been developing all of the systems that will go into this vehicle, including battery protection systems, vehicle control systems, telemetry gathering systems, along with power distribution and management systems. We've also been developing debugging tools to help us along the way. The focus on all of this has been to create a well-architected system that we can rely upon to keep our driver safe and our vehicle running. Moving on to the mechanical systems, like I said before, there's been heavy emphasis on weight savings and power efficiency. So we decided to use aluminum 6061 for our frame.
The shell of our vehicle will be using carbon fiber, which is a lightweight and extremely rigid composite material that we have worked with in the past. Our vehicle is a monohull design. Its single hull will be essentially one large cavity, as opposed to the catamaran style that the team pursued with our last design. The monohull design is easier to manufacture than the other alternatives, and we are confident that we can achieve excellent aerodynamics with it.
A lot of our members have also been hard at work developing the internals of the vehicle, such as the driver cockpit, the enclosures and mounts for the electronic systems, and the moving components in our car. The dynamic systems have also had a heavy emphasis on weight savings. Most of them are using 6061 aluminum, just like the frame. For instance, the steering, braking, and suspension systems. These are currently being manufactured in the ETC right here on campus, and we expect the components to be completed by the end of the semester. Looking ahead, next semester we want to shift our focus from manufacturing components to integrating all of these into a final vehicle. By spring of 2022, we will have a running vehicle, and by the summer of 2022, we will be ready to race in the Formula Sun Grand Prix. The team has been working really hard so far on all of these components, and we're really excited for the car that we're going to have. I'm going to pass it back to Michael now. See y'all.
Now I'd like to take a second and recognize some of our most generous corporate partners and advisors over the past couple years. First, I'd like to give a huge thanks to Toray Composite Materials for donating this year's and last year's carbon fiber. Next, I'd like to thank Jacob Kimbrough at Gurrit for his invaluable manufacturing advice. I'd like to thank Jeff Cloud at Bell Flight for his help in our last fall's design reviews, to Dr. Judy for her battery advice and general assurance that our car wouldn't blow up. Finally, to Dr. Gary Halleck, longtime friend and advisor to the team. He's been an excellent knowledge source on what past teams have done and has also advised on almost every component of our car. Of course, I'd like to thank our friends, family, and corporate partners for your continued support in our quest to build a car.
We're so proud to present our past year of work. These are the most competitive designs in our organization's recent history, and we can't wait to see how they'll perform on the tarmac. But we don't just build race cars. We're dedicated to creating the next generation of engineers, and we couldn't do that without the help and support of our partners. Specifically, I'd like to thank the Walker Department of Mechanical Engineering, Chevron, the Gene Haas Foundation, Cumberland Additive, and RWE for donations and help and support along this process. I'd also like to thank our faculty advisors, Dr. Ron Matthews, the founder of Formula SAE, Dr. Gary Halleck, and Dr. Neil Hall. Thank you all so much for your time and support. And lastly, I'd like to thank you all at home for watching us. We'll see you next year. Thanks for sticking around. We have a surprise for you. We've teamed up with a company called ViewZar to allow you to unveil our cars in your living room, on your desk, or even in your backyard. Just go ahead and scan the QR codes in a few seconds, or click the links in the description, and you'll be on your way. Thanks.